Hello and welcome to A Day in the Half-Life, a podcast about the past, present, and future of the science that shapes our lives. I'm Aaliyah Kovner, and in this episode, we're going to discuss something that truly impacts all of us, every day. It's so widespread, in fact, that the planet is literally filling up with it, and not in a good way. We're talking about plastics. There's no doubt that we need materials with the properties of plastics, materials that are inexpensive, durable, and highly versatile. But there's also no doubt that we need to get better at recycling and disposing of plastics. An estimated 300 to 400 million tons of new plastics are produced each year. Around only 2 to 8% of that is recycled at all. The rest goes into landfills, incinerators, or leaks into the environment. So we need to solve the problems with existing plastics, and for a truly sustainable future, we also need to begin a large-scale transition to new and improved materials that aren't made from petroleum and that are easier to break down. My guests today are three scientists who are making big strides to reimagine the plastics landscape. Welcome, everyone.
Hi, I'm Brett Helms. I'm a staff scientist at Berkeley Lab's Molecular Foundry, and my expertise is in designing plastics that are infinitely recyclable.
So I'm Ting Xu. I'm a senior faculty scientist in the material science division at Lawrence Berkeley National Lab. I'm also a professor in the Department of Material Science, Engineering, and Chemistry at UC Berkeley.
Hi, I'm Corinne Scown. I'm a staff scientist at Lawrence Berkeley National Lab, and I do systems modeling applied to, among other things, plastics, novel plastics, recycling processes.
So I'm really excited to have you all here together because I think there's a very important common thread in all of your work, which is a focus on developing products that are exceptionally functional and good for the planet long term. Just from following the news, I've learned that a lot of the products we have today either function fantastically, but we have to work kind of backwards or sideways to make the product's life cycle sustainable, or we create problems for ourselves in order to make the eco-friendly materials as functional as their conventional counterparts. For example, I recently found out that some of the popular plant-based cutlery and straws that I think a lot of us have used by now, they will biodegrade when you put them in the compost, but to make them usable, they've been formulated with harmful molecules that remain in the soil, air, and water for thousands of years after they've been composted. So there's obviously a lot of issues in this industry right now, and I was hoping to start us off, Corinne, since your work assesses the big picture for materials and product design. Can you tell us a little bit about how we got to where we are now, and why is it so hard to recycle plastics?
Yeah, absolutely. So we rely on polymers for all kinds of products that are really useful to us in modern life. And I should define polymers. Those are large molecules composed of many repeating subunits called monomers. And we'll use both polymer and monomer term throughout this discussion. But you can think of things like polyethylene terephthalate or PET, like plastic bottles that you use. Some of the clothes that I'm wearing right now are made out of polymers. And the reality is that we recycle a really small fraction of this material. So less than 10% of the polymers in our waste streams in the United States are recycled now. And for some polymer types, like polypropylene, for example, it's even less than that. Now, people think a lot about the single-use goods that we use, like food packaging, for example, because it's something that I think we think a lot about it as we are like using it once. You unwrap a candy bar or a bag of chips, and you just put that in the trash, and you think, oh man, that is going to persist in a landfill for a really, really long time. I think we all feel bad about that. The reality is that the breakdown of our waste it's really about half and half between single-use packaging and durable goods. And in fact, the durable goods are in many cases much, much harder to recycle than the single-use packaging. So a clear PET bottle is one of the most recycled items that we have in our waste stream. Certainly, in terms of the plastics or polymers that we use. durable goods, so think about like a sneaker. It's made of all kinds of different material that's glued or stitched together in a way that would be very time consuming and require a lot of labor to deconstruct into something that's reasonable to, say, melt down and use to create some other product. So this is part of why it is so difficult to increase that recycling rate. It's tough to get this stuff back. But even if you get it back, it's really difficult to kind of sort it out and isolate all of these different kinds of polymers that we use together for many of the products that are super useful to us. And so much of the recycling that we do today is really what we call downcycling. We'll take a product, we can shred it, melt it, kind of re-extrude it into a product, but that might still have dyes in it, additives, and it's a mixture of all of these waste products that have all been kind of tailored differently for their original use cases. And so what you get out has a lot of stuff in it that you didn't actually necessarily want. And so to achieve the same kinds of properties that you need, you very often blend that material with more virgin polymers. So you might only have like 10% recycled material in a product or 20%.
So little plastic even gets recycled in the first place. And then even if it does end up getting recycled, very little material is really being used more than once. Is that correct?
That's right. Every time you recycle the material, you degrade the quality. So the length of the polymer chains is important. And just like the fibers in your clothes, longer is better, longer is stronger. But over time, through sort of shredding, melting it down, reforming it, you end up with shorter and shorter polymer chains until you have something that is significantly degraded in terms of its mechanical qualities. So even if you didn't have the dyes and stuff in there, you can only recycle it for a limited number, let's say 5 cycles before it's just not usable anymore.
So, Brett, you're leading a group that is working to solve the issues from one half of the problem that Corinne was talking about, which is the long-lived kind of durable goods that are made from plastic. You're addressing the challenge by creating an alternative polymer entirely. What makes your plastic different from the conventional rugged plastics that we're using today?
Great question. So the types of plastics we make in my group address longstanding challenges in plastics recycling. As Corinne mentioned, when we mechanically recycle polymers, what we do is progressively degrade the materials to smaller and smaller chain lengths, and that affects their properties in subsequent manufacturing cycles. Polydiketoenamines, or as we call them for short, PDKs can be chemically recycled. This means that polymer chains can undergo a chemical transformation that reverts them back to their original monomers. These original monomers are essentially the raw materials from which the plastics were originally created. And that means that you can produce new plastics from the recovered monomers that have exactly the same properties as they did the first time you made them.
That's amazing.
So this chemical recycling advantage is something that opens the door to circularity in plastics, and the properties of PDKs are tailored for durable goods.
As a consumer who often feels guilty about the amount of plastic that I use, the idea of a guilt-free plastic is pretty compelling. So naturally, the next question is, how is the development going?
In the development of PDKs, what we have learned from our discussions with people in industry and with brands is that consumers are increasingly seeing the sustainability of plastics not only from the lens of recycling and circularity, but also through the lens of biorenewability. And so over the past few years, we have been working with scientists like Corinne and Jay Kiesling at the Joint Bioenergy Institute to create a biosynthetic pipeline for all of the raw materials used to create PDKs. And in this way, we bring biorenewable circularity to that platform and meet the expectations for both brands and consumers alike.
Yeah. One of the things that we talk about a lot as we devise strategies for moving away from our reliance on fossil fuels is the fact that we don't use the whole barrel of crude oil just to make liquid fuels, right? So about 80% of it is used for making diesel, gasoline, jet fuel, the things that you and I think of when we think about stuff made from petroleum. But then that other 20% is petrochemicals. And a majority of that are the building blocks that we use to make the polymers that we've been talking about today. So as we try to draw down on our reliance on crude oil, we also have to have renewable alternatives to the things that we make from petrochemicals. Sometimes those can be drop-in replacements. There are ways to make some of the same polymers that we use today from biological material. And in the case of the PDKs that Brett's talking about, these would be novel polymers that can replace some of the other types of polymers that we use today. So not only is it important for reducing our reliance on petroleum, but it also has this benefit of potentially reducing greenhouse gas emissions. That's because you're just bringing less fossil carbon into our carbon cycle. And if you're able to recycle this material over and over again, you can dramatically reduce the emissions because the recycling process, particularly associated with PDK, requires very little energy, very little in terms of other natural resources relative to, say, producing a virgin polymer from petrochemicals.
That's so exciting. It goes to show what an extremely well thought out and well designed product this is, that it's solving multiple issues of the plastics and materials pipelines. That's really, really cool to hear. Brett, in terms of bringing this to market, I mean, obviously it's still kind of early days, but how is that looking?
I think we're likely to see PDKs on the market and certain products, within the next 5 years. I think critical to that is, making sure that we can scale the production of all of the raw materials, ideally from these biosynthetic processes where engineered microorganisms are producing from various cellulosic sugars all of the molecular building blocks that go into PDK materials. So it'll be very exciting the next few years to advance those to scale, as they are pretty critical to this next phase of deployment.
So that's quite soon, actually. What's the target product that you're looking at, or target products where you're going to try to introduce PDKs to the world through?
Yeah. If you think about products where we have a good shot at getting that material back, and a large fraction of it, one of the ways you can try to do that is avoid the kinds of products that people will tend to throw in the recycling bin or in the trash. And so bulky items like mattresses, furniture, even some of the components of cars are materials that are really challenging to manage. Actually, mattresses are one of the most commonly illegally dumped items. And so it's clearly a problem, right? Like when you get a new mattress, you often pay a company to haul it away. And that industry knows that they need to increase the rate with which they recycle those items. And all they know how to do right now is downcycle it. And I really mean downcycle, like shred it up and use it as cushioning in like a dog bed or something. And so if we can provide a way to improve the circularity of that material, to actually break it down and then use it again to make a new mattress, that could have a really big impact. And so those are some of the applications where I think we have a good shot at getting a lot of the material back and actually getting it back into the same or a comparable product after it's been recycled.
Great. So let's talk now about the other half of the plastics industry, which is the single-use plastics. Corinne, you mentioned that some single-use items can get recycled pretty well, like the water bottles, but that a lot of them can't. To address this problem, people have developed compostable single-use plastics. However, as I think many of us have experienced firsthand, these compostable bags and forks and straws, they often start breaking down before we're actually done using them. And then I've read a lot about how they're also not fully breaking down when they're supposed to, when they're disposed of. So, Ting, I heard that you are working on making single-use plastics that are actually biodegradable. Can you tell us a little bit about your work and your enzyme-based approach?
What we're doing is actually very simple. If you think about the life cycle of the plastic in the wasteland, enzymes are the one who is doing the work. You can think of microbes, but really get down to the molecular level, you need all this enzymatic process in order to go through a chemical transformation. So if you look into the biodegradable plastic for single use, their production is huge. The only thing is that they are not doing what they're supposed to do, because when they were tested, they are in the test tube and there's plenty of enzyme or microbes available. So if you can simulate what exactly you have in the test tube in your wild environment, you are all set. There should never have a problem. The problem is it's just not degrading in the environment when you toss them away. So what we are saying is that if we take that biological process and embed them in the plastic from the get-go, then we are not limited to the availability of the enzyme. And then the second aspect is if we can control when, where, and how the reaction process is going to go, then we harvest the power of nature. And then we essentially can really, fulfill the promise we scientists made to the community at the first place.
Can you just tell me a little bit about how the chemistry of the materials you're making is both similar and different to what is conventionally being used in the stores right now?
How we do it is very simple. If you make a plastic, you need to put a little bit of pigment in there. The pigment get dispersed, and you make the whole plastic have a color. Imagine that pigment right now is the enzyme. So you just add them as you add the pigment during the manufacture. And the only thing is in this case, we disperse how the enzyme is being dispersed, and as well as where and when they can be triggered. So that's the part we provide. Other than that, we are not really doing anything new. There's no new chemistry. There's no new polymers.
Right, but you are able to make it work so that the bag doesn't start to biodegrade before it's supposed to?
Yes, that's exactly what our contribution. We control when and where and how. So we basically take advantage of the inherent property. Polymers is like long spaghetti noodles. And instead of the plastic bag, the spaghetti noodle are arranged in a certain way. You can just slurp from the end and then chew it up, and then you become these little pieces, and that's the small molecule. So by modulating the mobility of the pasta and modulating the availability of the mouth of the enzyme, you can modulate when the two is going to see each other. So that's the first step. A second step, you also have to think about the enzyme need to be motivated in order to chew up the pasta. That is a thermodynamics, right? It has to be a thermodynamic downhill in order for the reaction to proceed. But if you can chop it up into small molecule that can be dispersed, the system get happier because they gain more freedom. And that is a very important energetic contribution for us to provide a driving force for the whole process to occur.
So I'm curious, how far along in development are these products? Is it something that could be available and on the market soon?
So that's where one of my graduate students, Aaron Hall, just recently have a startup, and their job is trying to make this enzyme as additive to get into the plastic. The trick is that the enzyme has to remain alive. And the second is that the enzyme cannot be lumped together, because you really don't want your plastic bag to be 40% of enzyme for a 6% of your plastic. You want it to have a 1% or like 0.1% or like 0.01% of enzyme. And the second aspect is they need to be dispersed individually. So you need to make sure that every enzyme have a chance to see the plastic. So those two things are really bottleneck.
Right.
The key point is really based on this fundamental knowledge in nanoscience, that how you're going to keep this nanoscopic, only a few nanometer particles stay alive inside of this messy plastic instead of clumped together. Enzymes like enzyme, they don't like plastic. So for that, what we do is we provide a jacket. That's where we call it enzyme protectant. It's inspired by the proteins that is used to stabilize enzyme in their native environment. So we coat that on the surface of the enzyme so that allow us to keep them active and also help them being dispersed. And that also actually gave us another handle. You mentioned just now how we can control when they are going to start to chew each other. And the outer jacket is another handle that we can use. Because what happened is that you cannot just have a one particular handle to modulate the degradation onset. You need to have multiple ones. So when you think about the environment and the conditions it need to be used, is a fairly diverse and it's fairly unpredictable.
Okay. And when these enzymes are cued and when the conditions are right and it does break down those polymers, I mean, the polymers are ending up, they're turning into monomers that are safe for the environment and non-toxic?
Yeah. What the polymers break down into depends on what you've put the enzymes in. So a really common compostable plastic that Ting's group is working on, and we're collaborating with them, is polylactic acid, or PLA. So PLA breaks down into molecules that are commonly available in the environment. You don't have to worry about them. The only polymers that we need to pay special attention to are the ones that don't necessarily exist in the environment. So these kind of jackets or the coatings around the enzymes, try to pay attention to what those break down into. So one of the things that you can do is do accelerated aging and collect sort of what comes off of the polymers and see if there's anything of concern. So this is a fun collaboration that we've had where we can do kind of toxicity screening for all kinds of different molecules and identify if there's anything that we would be worried about. But so far, we don't have any concerns about how these would break down at a composting facility. Everything that they break down into would be stuff you would find in the environment anyway.
That's amazing.
So the jacket is UV degradable. That's part of the reason why we select them. So they naturally degrade when exposed to UV light.
And so is this something where, like, looking at the industry, is it going to be able to be competitive with existing biodegradable plastics and existing single-use plastics? Corinne, you look at things like the economics of an entire process. Is this something that you think is going to be appealing and cheap enough to make that it could really replace the existing stuff soon?
So remember I mentioned to you about this nanoscopic dispersion of the enzyme? So for the project we're dealing with, the whole thing is less than 1%, including the jacket and the enzyme. The jacket is not expensive. The most expensive part is enzyme, but we can go as low as a 0.02% by weight.
Wow.
Yeah, Ting's exactly right. Enzymes are the expensive part in this process, and there are actually processes being commercialized now where instead of trying to put the enzymes in the polymer like Ting is doing, they're actually trying to break down the plastics like in a reactor with enzymes. So you sort of adding the enzymes later in a solution and using those to depolymerize the PET, for example.
Right.
So I think the beautiful thing about this strategy is that you can use way less of the enzyme if you embed it into the polymer, as opposed to sort of adding it afterwards in a reactor and trying to get it to break the polymer down from the outside. So anywhere between, as Ting said, 0.2% up to kind of single digit percent, depending on the polymer that you're creating. The contribution on the cost is pretty minimal. So the enzyme itself is a really small fraction of the mass, and then you have this larger contribution from these kind of jackets that she talked about that protect the enzyme. So we've been modeling how you would produce those clusters and then how they get embedded in the enzymes, and they're very competitive. The costs are not that different than the sort of typical polymers available today.
So essentially each product that you're making is its own little recycling factory in itself, little jacket-wearing enzymes ready to go, which is pretty neat. I love that idea. Instead of having to have, all these facilities that cost money and electricity, it's like, nope, I've got everything I need right here, thanks. And I immediately think, of course, there's a lot of different environments where this needs to happen, which you alluded to, Ting. Have you had some really fun field work where you're going and like stuffing these products in like this kind of mud and then in like this kind of water and like put one up in a tree? What has that part of the process been like?
My student made a home composting. So
Nice.
this is during pandemic, right? So they get the dirt and they look at the standard how you make the composting composition. So they did that, and along the way they also tried just use warm water. Those are the two things that I find is quite interesting, right? And I think the tunability is something that we are really proud of. And I think give us a lot of options to modulate the formulation, the process for different environments. So I think there's still a lot of work need to be done, but I do think we have a very good uh, foundation because we were very fundamental.
Yeah, so when we were planning this collaborative project, we got a commercial composting facility on board. And so they've agreed to test some of Ting's material. And we're really excited to get it out into those composting windrows because a commercial composting facility can be very different than a home composting in terms of the temperatures, the residence times, et cetera. But if this material breaks down successfully at that facility, and I have no doubt that it will, I think that's going to be a really big deal because polymers like PLA do not break down well at composting facilities now. It's something that people in the organic waste management industry complain about constantly, that some of these compostable plastics just don't break down. So that's really interesting. And then the other thing that I would love to see is if it's possible to tune this material to break down in anaerobic digestion facilities. So there's a facility down in San Jose that we worked with that does so-called dry anaerobic digestion. It's not really dry. It's actually still very wet, but they take municipal organic waste and put it in these big digesters with percolate, get the microbial community going. And they would also complain about compostable plastics coming out exactly looking the way that they came in. If you could get, say, food packaging, where when a grocery store has food that goes bad and they haul it to a facility like the dry facility in San Jose, like if that packaging can just break down easily along with the food, that makes it easier to divert not just the plastic from the landfill, but also all of that organic material that we don't want to go to landfills because you can get energy out of it. You can also get nutrient rich compost at the end of the day.
I'm really struck by the fact that everyone on this call is making products very intentionally, where from the very beginning, you're looking at all the pros and cons of many years down the line, many different circumstances. And it's amazing, but I understand that this is a pretty new design philosophy for the materials world. And so, what has it been like to try and take these inventions from lab scale discoveries to the next stages, which it sounds like you're both in that process. You're both beyond the lab scale already, and try and get them scaled up for deployment in the real world. Has there been a lot of pushback from the commercial and industrial entities you're trying to partner with, or from, even like the municipalities who you would need to work with? What has that been like? What has the kind of atmosphere been like for you?
Thanks for that question. I'd like to answer it by first making a little bit of an observation at a high level. So brands across the world and plastics manufacturers have been making promises about the sustainability of their products as well as their future goals for sustainability. And when you look at the foundational chemistry of the polymers, the products that they're used in, whether these products will be composted, whether they will be recycled and remanufactured on that basis, I think what we are realizing very quickly is the materials that we have today and the processes that we have available to us for composting and for chemical recycling are inadequate to reach our sustainability goals for the future. This has been the sort of basis by which, researchers like Ting and myself and all of our students and postdocs, this has been the basis for change, right? This is how we justify what it is that we are researching to provide that vision and opportunity to achieve our sustainability goals in the future.
And would you say that it's, you're starting to sort of make progress and that people are willing to invest more to make those changes, to have like circular products that are truly recyclable? Is the movement growing, I guess?
I think the movement is growing in the sense that there is growing awareness that new materials are likely going to be the tipping point to move us toward a more sustainable future. I think there is growing awareness that we are a part of an ecosystem, and innovations that are happening at Berkeley Lab are likely going to be paired with other innovations in the recycling system as a whole. So, from my perspective, I think this is a really interesting time to be thinking about partnerships, right? So, some of these partnerships are being built up. As Corinne and Ting mentioned, we have closer ties to people actually recycling plastics. We have closer ties to people that are attempting to compost plastics and recognizing their challenges. And these are people that we've been able to pull into our sphere of influence to get them to work with us to, de-risk and mature the technologies for their intended use. And I think that is unprecedented, that level of public-private partnership, particularly in the fields of plastics. I would also offer that companies in the past, particularly those who produce plastics from petrochemicals, have not really emphasized in their business building any of these, circularity principles, right? Whether we're thinking about, circularity in the ground or circularity in chemical recycling, and I think even they are recognizing that we are in a moment of change, and they're coming to the table not only with their resources and talent, but they also have partnerships that they have developed that are likely to be, critical for large scale deployment as well in the future. And I think there's a lot we can learn from each other.
I think I agree with what Brett has said. And in our experience, what we see is there's a lot of interest from the consumer end. And I would say there are economics any business will consider, but I think the biggest driving force is really coming from the consumers. The consumers have forced the industry to make a change.
Right.
And it's not like I don't give industry credit, but by the end of the day, they have to be responsible for their investors. Right. So while there is a need from the public, especially the millennials, they wanted to pay a little bit extra to be environmentally responsible, and that has been a huge driving force. So I think the more the public wanted to voice their opinion and wanted to use their power, the better chance we're going to have a great future.
Yeah, I think we're about to see a huge change in the way that we design and use polymers. The polymers of the past have been designed to be stable when we need them to be, and that's it. The polymers of the future will be programmed to be stable when we need them to be and break down when we need them to. That is the fundamental shift that we will see, and it's going to enable us to deconstruct and separate all of the different components of the products that we make. And it's not just about enabling better polymer recycling, it's about enabling better recovery of valuable metals, all kinds of things that are in our consumer electronics. It's about making it easier to divert our organic waste from landfills. All of these things can happen if we just make it easier to deconstruct and separate all of the different polymers that are inextricably integrated into just about everything that we use now.
Yeah, I think that's a really good point. We've sort of been focusing on like, here's just the plastic breaking down, and we're worried about that, which is valid because there's a lot of materials, there's a lot of things around us that are just mostly plastic. But it's also, our the laptop I'm looking at, my phone, parts of my car, my clothing. It's all other materials that we also want to be able to recycle better. But first, we have to get over this hurdle of the plastics that are mixed in with them. So I think that's a really good, thing to highlight as well.
Oh, I think the plastic recycling is just a start. Because by the end of the day, if you think about it, there are elements in the periodic table. We take them from nature through mining, which is environmentally harmful. And now we're getting to a level that even you want to pay the cost for mining, there's not that a lot. And you should really start to mine from your waste.
Right.
I would add that we are often thinking about what our future looks like. And to the extent that we have discussed today, we've considered how is it that we make a future world where plastics are part of the solution and not part of the problem. And I do think that when we map forward how we will use plastics in the future, we need to recognize that there are a wide variety of technologies that utilize plastics. And if we manufacture them with, the plastics of the future, that has the ability to bring sustainable circularity to those products. So when we think about, you know, smart textiles and wearable electronics and all of the things that we know and love about visions of the future, these things are actually happening now. We are designing materials for those now, and understanding that they will be commercialized 10 or 20 years from now. If we make the wrong choices now about what plastics to use in those products, we will have done a disservice, right, to future generations. And we will have ignored everything that we have advised ourselves of about the mistakes of the past. And I think now is a really important time to bring, all of the relevant stakeholders to the same table and work together. I think it's a fantastic time.
Yeah, it takes coordination across all of these people in the supply chain. I think that's one of the challenges that we have to overcome is that if you design a product to be more recyclable, then you have to find a way to get it back so you can recycle it. If you design a plastic to break down well at a composting facility, then it has to make it to that composting facility. If it goes to a landfill, it doesn't help us as much. And so we all kind of have to hold hands and jump together. And it's easy for any one person in that chain to kind of point to the others and say, yeah, but unless they do their part, then this isn't going to work out for me. And we have to change that mindset and say, we are all going to figure out how we contribute to making this vision work. It's tough to coordinate, but it's necessary. And as Brett pointed out, there's a lot of motivation on the part of the public and consumers to help make this work. And I think once you have that, that's all you need.
So I'm wondering, as a non-scientist myself, and for listeners, what's sort of like reasonable thing that consumers can do? I mean, there's a lot of greenwashing out there about recycling, about how much recycling is happening versus the reality of it. And then there's a lot of products that, aren't quite yet on the market yet that I would certainly support if they were ready. Like, please let me know when I can buy some PDK shoes. I'm all for it. But, I guess it'd be nice to sort of end with something that is some practical advice for consumers of how we can keep being that positive driving force on the industry.
That's a great question. Certainly in a lot of cities, composting is becoming possible. So you can always kind of check the labels and try to put the biodegradable stuff in your compost bin. You can be mindful about what you put in your recycling bin. I always hesitate to tell people recycle more because the recycling facilities get a lot of things that they say are, quote, wish cycled. I've seen Mylar balloons show up. I mean, there are all kinds of crazy stuff shows up, and they'd really rather that people go ahead and put those in their trash because it makes it harder for them to get the material that actually is recyclable out. But I also think that some of these companies that you buy products from that are not recyclable, they need to hear from you. They need to know that their consumers care about what is going to happen to those products at their end of life. And so even just inquiring at like a brick and mortar store, hey, you guys have a take back program? What am I going to do with this product when I'm done with it? I think that would make a big difference, because the more they hear that, the more they will realize that it matters to their consumers, and it may motivate them to do more than they would otherwise.
I agree. I think, the most that we can do as consumers is, use our buying power to indicate what we want in future products. I think that brands look at these numbers and they establish, an understanding of the growth of certain market segments that may emphasize, for example, more sustainable products, and that those business models are actually profitable. Like that's what we want to see, from the business side of things before we make decisions about disruptive change, right? And it will be interesting to see how that plays out. Specifically, we lack the ability as consumers to, identify a product as sustainable, right? We have been lied to for generations that all plastics are recyclable based on the label that we see, right? Where you see this recycle symbol and maybe a plastic number, right? And there's the underlying assumption that that little recycle symbol means that that product is something that can be recycled. This is exactly why we have issues with wishcycling in the current way that we manage plastic waste as consumers with, various municipal waste processing facilities that are now struggling to deal with all of that. So I think that there is a growing understanding that that is a misrepresentation of what can and should happen to plastics. And I think the labeling strategies will change. And I think that when shopping and, choosing something off of a shelf, we can look at it and have more knowledge about the recyclability of those products. The second part, I think, that requires a little bit more work is, how do we know that the products that we are buying have been made with recycled materials, right? What are the strategies that we do to ensure the provenance, right? The traceability aspects of plastics as they move through, secondary manufacturing cycles where circularity is the intent, but how do we certify the content, the recycled content in products, particularly if they're recycled over and over and over again, right? And I think what you're likely to see is, a complete, digitalization of the recycling industry to enable traceability and help us monitor and track our progress on these sustainability goals for increasing recycled content, increasing biorenewable content, increasing compostability. All of the things that we've discussed are absolutely important for plastics in the future.
I think what we really should think about is that each of us serve multiple roles, and you just have to practice in each role you're serving. Corin basically saying that we should practice recycling daily. That's what I think is important, because by the end of the day, we are the one who create the mess, right? We create the plastic, we use the plastic, and we toss them away. So I think it's important to understand not just about we talk, we want to recycle. It is really, we are the problem creator and we should be the problem solver. And then as a consumer, you certainly have to use your power, because economic wise, it's just that the table doesn't turn by itself. And I think one thing is that you have a very positive tone toward the recycling, but there are always people who just don't see value in there. And if they don't feel like their opinion get represented in this, then they would just not go in. And those are the sectors you do want to get them. You sort of have to embrace their opinion and try to gradually ease them in.
It's true. I mean, I thought about mentioning how when I found out about how much plastic is wish cycling, how I fell into a plastics funk and was like, none of this matters. I don't even care anymore. And I just threw it all in my garbage. And I was like, I was lied to as a child. But I think that's an important point. It does and you get really overwhelmed, and you start to think like that it doesn't matter. And I think it's a good point. Sometimes the more you know, that you get more overwhelmed. There's like this weird kind of hump where like you don't know anything, so you think it's fine, and the more you learn, you're actually more concerned. And it's only when you know a lot that you're like, okay, wait, things are getting better. So I think that's a valid point. There's probably a lot of listeners who follow the news and are still feeling quite pessimistic about it. So, yeah, I think that's a good point. And is there a message we should give these people?
The other thing is actually equally important is that we polymer scientists may be viewed as a villain for the society. People is like, why in God's name you starting this out the whole thing? We can use banana leaf to wrap food, and then we can use cloth bags to taking things. You guys are terrible. You brought us to the mess. Anyway, I'm just leaving things on the table, just to let you know, for the sake of a diverse opinion.
I like that.
Yeah. I mean, honestly, I would tell people, like, it's okay if you find this confusing. Like, that when people ask, like, well, what should I be putting in my recycling bin? The answer they get most commonly is, oh, call your local recycler. And I just think,
no one's going to do
oh,
that.
yeah, with my abundant free time, like, I have 2 kids. I'm not going to call up my recycler. And it changes. One thing I noticed in tracking the prices of recycled material is that it fluctuates wildly. And that's part of why it is so confusing, because literally from one year to the next, I've heard, oh, we never pull out polypropylene, to now all these recycling facilities are pulling out polypropylene. That's number 5, right? They always pull out ones and twos. And now I'm hearing that a bunch of them are adding a quote unquote line to take out number 5, polypropylene. And so I used to put polypropylene in the trash because I said, oh, that's wishcycling. And now I'm like, I better put it in the bin. So you don't have to feel horrible about this. It is really hard to keep track of like what to do to be the most responsible recycler that you can be. I feel like we haven't talked at all. Like when you ask like what people can do, you can also reduce your use of particularly single-use plastics.
I've heard it often described, use less, longer, and smarter. And I think the smarter part is really what we've, discussed at length, right, in this program, right? And smarter comes from an understanding that the foundational chemistry of plastics can be, approached from a smarter perspective. The way that we think about sorting and recycling can be thought of with a smarter perspective. Now that we have this abundance of knowledge about what we want in the future and how it is that we're going to get there based on a roadmap that brings everybody to the table. So
cool. I like that. That can be the 21st century replacement to just reduce, reuse, recycle. It's a little bit more informative.
I love it.
I think.
Yeah.
I guess I would add that, we should advocate for upgrading the recycling infrastructure locally, and also appreciate, if any positive recycling innovations can be more broadly distributed across the U.S. I think if we want to recycle more, we need better sorting facilities. And I think that is something that will take a little bit more work, right? It's expensive currently to do recycling.
Right.
However, we've seen a really interesting connection point between artificial intelligence and robotics and ways of rapidly picking out, specific plastics on manufacturing lines at high rates. And these types of advances, whether they're for existing plastics or future plastics, are likely to be the way that we do this in the future.
Yeah, there's a lot of cool technology being developed to make it easier to separate these products out and get more pure bales of recyclable material. And we have a long way to go. But I think if we invest in the infrastructure to make it work, we can leverage the traditional mechanical recycling that works in some cases alongside some of these more advanced processes and kind of swapping in novel polymers. It's going to be a portfolio of solutions. There is unfortunately no one silver bullet that's going to solve all of our problems.
Right.
But if we put these things together, we can get pretty far.
So like an existing recycling facility with better sorting features, maybe an AI-driven sorting feature, could learn, for example, to remove a piece of PDK when that comes on the market. Like, oops, this is in the wrong place. And now it's going to get separated and it's go to the place where PDKs can get infinitely broken down, or can separate out, a PLA that has the enzymes in it to a compost facility. So I think that's a really good point to make, that upgrades in one part of this industry will benefit the whole industry.
Yes, exactly.
And I also just think it's nice for people to hear from you all that, like, yeah, this is confusing. It's like, yeah, there's not a lot of transparency sometimes, but we know that, and that we're working on it. And, there's still a lot of innovations happening despite those challenges. So thank you all so much for being here and for this really interesting discussion of where this industry is going. And I think that like you mentioned, there are a lot of challenges, but there are a lot of reasons to be optimistic. So thank you all so much for your time.
Thanks for having us.
Thank you for having the opportunity to share our thoughts.
Thanks again for bringing us together today.
Thank you for listening to A Day in the Half-Life. I hope this episode helped ease some of your plastic-related dread, as it did for me. But of course, the problem isn't solved yet. So let's all keep doing the best we can as consumers. Now, excuse me, I've got to go take out my recycling.